Welcome to ePassara lecture series on computer science. We are discussing about the paper Cryptography and Network Security. Today we are going to continue the topic Algebraic Structures. The objectives to review the concepts of rings and fields. The last session where we discussed about groups and also some of the examples related with the groups, subgroups, cyclic subgroups, and also we have discussed about the order of a group. In continuation with that, we are going to discuss in this session about the rings and field, and also we are going to discuss about the finite field, the purpose of finite field in the field of cryptography, and the concepts related with the cryptography where we are going to perform an modulo prime operation related with polynomial with the help of Galois field, and also we are going to discuss about some of the Galois field with an example. The keywords are ring, field, finite field, Galois field. So, this slide is explaining about what is an algebraic structure and also what are the structures we are going to have. In the previous session also we have seen this particular topic. In this we have three, already we have completed the groups. Now we are going to discuss about ring and field. So, what is a ring? What is a group? The last class last session where we have discussed about the groups. In that continuation we have rings. The ring is nothing but where it has a set of integers with an operation, and where I have two operation in this. Okay, the distribution of one operation over the other, then I can able to say that I must have the following property to be satisfied. One is closure, associativity, commutativity, existence of inverse and inverse. So, these we have discussed in the previous structure in the group, where it should have 5 property to satisfy. Whenever I take any particular operation, we also worked with an example where I taken a one operation, either an addition or multiplication. From that I am able to find out whether a particular set of integer can able to satisfy all the 5 properties. Then the structure we call as a group. In addition to that, here we have the two operations. Only you can say that okay, this dot and the square. So, when I am taking this operation, the first operation must satisfy all the 5 property, and second operation the 3 properties. Let us take closure, associativity, commutativity, then I can say that structure is a ring structure. So, here is given an example. Let us take a set of ABC and the operation where I have dot and the square. So, when I am saying a particular operation over another, it is a distribution ring. So, example for a ring where we have set Z with 2 operations, addition, multiplication, then it is a commutative ring. So, last class also we have discussed, last session we have commutative group, that is your abelian group where it is satisfying the commutativity. So, it is showing the case R is the denotation for the ring where it has a set of integers Z and addition, multiplication, the 2 operation. So, if I take this structure, I say that addition will having all the 5 property and the multiplication should have the 3 property. Then we can able to see that then closure, associative and commutative, the second operation. The second operation in this particular example is multiplication. So, the multiplication only satisfy 3 property, whereas your addition will satisfy all the 5 property. So, when I have such a structure, then we can able to understand the particular structure is a ring. The application of ring over the cryptography is generally we use this ring in the case of our key exchange algorithms. The next structure and also most commonly used in our cryptography is field. A field is denoted by F is equal to the set of integer and the 2 operation dot and the square. It is a commutative ring in which the second operation satisfy all the 5 property defined for the first operation, except the identity of the first operation has no inverse, except the identity of the first operation has no inverse. That is, when I take 2 operation, let us take the previous ring structure. Similarly, here also we have set of values like A, B, C, and we have 2 operations, okay, dot and the square, when I take a particular operation is going to be distributed over, then the first operation should satisfy all the 5 property as like your group, as like your ring. Now field is also the first operation is going to be taking all the 5 property. The second, here the condition is the second operation must also satisfy all the 5 property defined for the first operation, except the identity of first operation have no inverse. The identity element of first operation have no inverse with respect to the second operation. That is the only exception when you compare to two operations which are going to perform with your field structure. And we have 2 different type of field. One we can call as an finite field, another one is an infinite field. So in cryptography, majorly we will discuss with the help of your finite field theory. So here we consider the Galois is a person who showed that for a field to be finite, the number of elements should be p power n. So finite field is going to be a part of any cryptographic algorithm. For example, if I am going to have a symmetric cryptographic algorithm, in the symmetric cryptographic algorithm where when I am going to perform one particular stage in AES, where I am going to apply this finite field for computing the result for the next stage. So the finite field where it is given by the Galois, where he states that number of elements should be p power n, where p is your prime and n is the positive integer. So we simply say that GF, so Galois field, since it is showed by Galois, it is given a name as Galois field. So GF p power n is a finite field with the p power n elements. So what is a Galois field? It is a finite field, nothing but GF of p power n. This is the finite field with p power n elements. So why we want to take this particular Galois field in the case of your cryptography is where we were going to deal with the binary digits. It is very much important to represent the binary digit with respect to the finite field. So we want to represent them in the case of your p power n. So we say that whenever I have a Galois field of p power n, then there is a finite field with a p power n element. So finite field, hereafter we can say either a finite field or we can say a Galois field. So Galois field, a finite field plays a key role in cryptography, as I already mentioned, where when symmetric cryptography, where we use this finite field for computing a value. So this we can able to understand, suppose showing a number of element in finite field must be the power of the prime, that is whenever I am going to take a number of element in a finite field, it must be power of p power n. So it is known as Galois field and is always denoted by GF of p power n. So what are the other, okay, the particular option used in fields are GF of p or GF of 2 power n. So here GF of p, where it is going to be in the case of when I am going to take a whole number, 2 power n when I am going to consider the binary numbers. So GF of p is a set of integer. So like what we had in the previous group and ring structure, either we can take a set of integers or we can say the integers with 0 to p minus 1. So here we can able to see that when I am going to represent a value in a binary, either I can able to represent with the help of GF of p power n or I can say that GF of 2 power n. So when I am going to represent with GF of p, then I can say that Galois field of p, in Galois field of p, what are the things I am going to have is set of integers 0 to p minus 1. You know what is a p? It is a prime number. So with an operation of arithmetical operation modulo prime p. So when I say GF of p, what is GF of p? Is a set of integer which are lesser than p and arithmetical operation with the modulo prime. These form a finite field. So since have a multiplicative inverse and we also find the inverse with a extended Euclidean algorithm, where we discussed in the case of your previous topic, we can do a addition, subtraction, multiplication and division without leaving the field, that is GF of p. So whatever the operation, since it is mentioned as modular operation, so whatever the operation we are able to say that here either I take an addition or subtraction or multiplication, division, So, without leaving the field, that is gf of p. Gf of p, for example, if we take when n is equal to 1, we have gf of p field. This can be set of zp which start from 0 to p minus 1 with the 2 arithmetical operation. Then we can say that is a Galois field of, okay, where it is taking 2 operation, that is addition and multiplication. Let us take this example where you can able to understand how this Galois field is going to be performing 2 operations. So, that is what it is given here. When I am taking gf of 2, right, 2 is nothing but what you have here is gf of p. So, if I am taking the 2 with a set of, it has 0, p minus 1, where p minus 1 is 1, and there are 2 operations. Let us take addition and multiplication. Now, we can able to understand with the help of this figure. It is explaining about when I say gf of 2, where I am having a set of 2 values, zeros and p minus 1, that is nothing but 1, and the 2 operation addition and multiplication. Now, what is happening, you can able to understand from this, where it is going to say that when I am performing an addition operation, where I am taking 0 0 0 1 and I take that 0 1 on the row and 0 1 on the column, then I am doing an addition operation. Let us take 0 0, I will get 0, 0 plus 1 I will get 1, 0 plus 1 I will get 1. When I am taking 1 plus 1, okay, as it is going to be mentioning, right, binary and the case where you can able to see that it is going to be like an, whenever you are going to perform an addition or multiplication, this is not an actual arithmetical operation like your addition or multiplication. We have to perform an XOR operation. So, what is an XOR operation? When I am taking 2 input, I am going to get 1 output with the XOR operation. If both the inputs are same, I will get, okay, let us take for example, I am going to take 0 0, I am getting 0, 0 plus 0 I am getting 0. If I am getting 0 plus 1 I am getting 1, and 1 plus 0 I am getting, then I am taking 1 plus 1, let us take I am getting 0. Similarly, if I go for, so what is happening here, 1 plus 1 with respect to 2, with the help of a value where I am not going to get 2, because modulo of 2 is 0, 2 modulo of 2 is 0. So, when I am taking that value, so 2, 1 plus 1 I will get 2, 1 plus 1 I will get 2, then I am performing mod operation, I will get 0. So, 2 mod of 2 will get 0. Similarly, when I go for multiplication, no, there will be 0 into 0, 0, all the value if it is going to be multiplied 0, you will get 1 into 1 mod 2. So, here you need to understand one important thing is, whatever the operation we are going to perform with respect to modulo of n. What is the n here? Here the n is 2. So, when I am performing an addition, okay, I am going to add the 2 number mod 2. Similarly, I am adding 0 plus 0 mod 2, 0 plus 1 mod 2, 0 plus 1 plus 0 mod 2, 1 plus 1 mod 2. So, 1 plus 1 mod 2 will get 0, that is 2 plus 1. When we are going to find the inverse with respect to addition, right. So, A, if I am going to get 0 1, inverse of that is when it is 0 you will get 1, when it is 1 you will get 0, okay, that is additive inverse, or where you are going to perform a inverse of addition operation. Suppose I am going to perform a multiplicative inverse, 0 there is no, okay, we are just putting an hyphen to say that there is no specific inverse for 0, for 1 we will get the 1. So, that is your, what I am trying to say from this is identity element, what is going to be given with this help. So, this is the way when I am going to represent a Galois field of 2 with a set of 2 operation, then how it is going to be resulting, which will be helpful to understand the larger value of p. Similarly, we will work on that example here, gf of 5 on the set z5. So, that is here 5 is a prime with addition and multiplication operation, where you can able to say that my Galois field have, what is that Galois field, which will have a set of 0 to p minus 1 and 2 operation. Let us just see the diagram where you can able to see that we have 0, 1, 2, 3, 4. So, that means 0 to p minus 1, 5 is p is equal to 5, minus 1 will get 4. So, there are 5 elements and we have two operation, addition and multiplication. Now we look into that as what did in the same example in the previous section, where you can able to see that when I am going to add the value 0 plus 0, I will get 0. The interesting thing is when I am going to add 2 plus 3, you can see that it is 0. Similarly 2 plus, so this table, right, it is explaining about how an addition operation is performed with respect to modulo of 5, modulo of 5. So as we can see that 2 plus 4, 6, 6 mod 5, we will get 1, the remainder is 1. Similarly 3, if you take for example 3 cross 3 into 3, third row and third column, what is the value we are getting? 1. How we are getting 1? Because 3 plus 3, that is 3 plus 3 is 6. 3 plus 3 is equal to 6 mod 5 will get 1. Similarly we do in the case of your another operation, that is your multiplicative operation, that is where you can say that when you are 0, all the values are 0 along the rows and columns, whereas you can able to take, for example, I want to go for 4 into 4 mod 5, 4 into 4 is 16, mod 5 is 1. Similarly you can able to see that 4 into 3, you are getting 4 into 3, 2, because 12 mod 5 will get 2. So whatever this table is explaining about the Galois field of set of z element with respect to addition and multiplication. With again there is another two interesting thing is, one is additive inverse and the multiplicative inverse. So when I am going to perform an additive inverse for the element, let us take a, right, a where I am going to take that 0, 1, 2, 3, 4. Suppose I am going to find the inverse of a, 0 inverse 0. What is mean by inverse? When I am performing a plus minus a, I must get the identity element. For example, if I take 1, for example, if I take 1, what is the inverse element of additive inverse of 1 is 4, because how we got 4? Because 1 plus 4 is 5, 5 mod 5 is will get 0. Similarly you take 2, what is the inverse? 3. Why you are getting 3 as inverse? This is your actual input. What is the inverse value is given in the second row. The first row is input, second row is giving the what is the inverse of the corresponding value. Similarly if you take 3, 3 plus 2 is 5, so we are taking the inverse, 3 plus 2 is 5, mod 5 is 0. So this is the additive inverse. That means if I take for encrypting with the with this value, I can able to decrypt with the help of the inverse value. That is the importance of inverse. So similarly if you go for multiplicative inverse, as a where you have a inverse, this row will have all the elements 0, 1, 2, 3. Now we want to find out the a inverse. What is the a inverse of mod 5 is? For example 0, we are not going to have any value because we can't find the inverse. Then you take 1, 1 inverse mod 5 is 1, 2 inverse is 3. How you are getting 3? Because 2 into 3. What is 2 into 3? We get 6, 6 mod 5 will get 1. Similarly 3, what is the value? 2. 3 into 2, that is 6 mod 5. So whenever I am going to perform these two values, that is a value and their respective inverse, we are going to multiply that, they should result with the identity value when I am going to perform a modular of that particular value. So that is what we can able to see, that 4 is, what is the inverse of 4 is 4, because 4 into 4 16, mod 5 is, that is 1. So all these are going to be identity element. Similarly we can also able to look out with the example for 7. Quickly we can able to see that same, just cross check 6. 6 is going to be where you are going to have 6, and in the case of your 6 into 2 12, right, mod 7, that is your 5, and similarly 6 into 3, that is 18, 16 into 3s are 18, mod 7 will get 4 because 14, right, remainder is 4. Like that we can able to solve this. So now we are coming to the polynomial arithmetic. So why you need to know about the polynomial arithmetic? Because so far we have looked into the integer, but our computer, when I am going to perform a cryptographic operation, normally I will do with the binary values. So how I can able to make the value to set with my computer? In that case I am going to represent with the help of polynomials. The binary values are going to be represented with the polynomial. For understanding that, we need to understand the polynomial arithmetic. So can compute using polynomial. So let us take an f of x is a function, and we can able to say a n x power n plus a n minus 1 x power n minus 1, like that you can able to say that plus a, which is equal to summation of a I x power I. where I can be 0 to n, that depends upon what is the size of your polynomial. So here it is going to be a specific value, not interested in a specific value of x, and which is also known as the indeterminate. So several alternatives are available: ordinary polynomial arithmetic, and also polynomial arithmetic coordination with a mod p, polynomial arithmetic coordinated with the mod p, and polynomial mod mx. Okay, so we are going to understand how we are going to use the polynomial. Before going to use the polynomial, we need to understand ordinary polynomial arithmetic. So addition or subtraction correspond to coefficients, not with the terms. So remember that when I take a polynomial, we are very much concentrating of performing an operations over the coefficient. Multiply all terms by each other. So for example, if I take f of x is equal to x cube plus x square plus 2, and g of x is going to be x square minus x plus 1, when I am going to add these two, f of x plus g of x, so I will get x cube plus 2x square minus x plus 3. Similarly, I am going to take a minus, I will get x cube plus x plus 1. When I am going to multiply that, so when I am going to perform a multiply, we have to add the power, right. So if we take first x3, we will perform multiplication of this one, and we will take x2, we will perform multiplication, that is from f of x, we will take the second term and we will perform the multiplication of this, and then finally we will simplify it, then we will got this particular answer. So when I am going to perform my multiplication, I will take the first term, I will do a multiplication. So for example, if I take x cube means x power 5 minus x4 plus x cube. Then similarly I will take x square, I will take x multiplying with this g of x, I will get x power 4 minus x cube plus x square. So like that I will take 2x square minus 2x plus 2. Then I will start to cancel, that means remove the term where I am going to get the final result as x power 5 plus 3x square minus 2x plus 2. Now we are coming into the modulo coefficient. So that is what the previous is explaining about a normal arithmetical operation. Let us take addition, subtraction or multiplication, which is going to be reflecting over your polynomial. Now when with the modulo coefficient, how we are going to deal with that? Because in your cryptography where the modulo operation is going to be used, so when you are computing a value of each coefficient, do calculation of modulo some value, it forms a polynomial ring. So we can say that it could be a modulo by any prime. Just think about that, it is going to be modulo any prime. So what if you are going to taking that particular case, for example, we are the most interested in, always we are going to work with the mod 2, because all the coefficients what you are going to deal with the this particular cryptography where you say that 0 or 1. If you take a binary digit, all the values is going to be deals only with the zeros and ones. So most interested is mod 2. So let us take this example. For example, I am going to take x cube plus x square, this f of x, there are two functions I am going to take it. One is f of x, another one is g of x. So when I take this, adding these two, so I will get, you can able to see that, right, x cube plus x plus 1, when I am multiplying that, x power 5 plus x square. So after simplifying, for example, x cube, x power 5, let us take this, going to be added. So this x square and x square are cancelled. When I am going to perform, then same term, because it is going to be 0 and 1, and you can able to see that from we are going to add the two functions f of x and g of x, we will get x cube x plus 1. Similarly, f of x into g of x, we will get this, okay, so x cube where we are going to get x square plus x square. So can write any polynomial in form, okay, for example, f of x is equal to q of x and g of x plus r of x. Can interpret r of x as the being a remainder where r of x is equal to f of x mod g of x. So if we have no remainder, say g of x divided by, if g of x has no divisor then other than itself or 1, then we can say that function is a irreducible polynomial, that is your prime polynomial. So we know what is a prime number. A prime number is a number which can divide by either by 1 or by itself, then we can say that is a prime number. Here also in the case of your polynomial, when I am going to take a particular function, for example, if I am going to say r of x is equal to f of x mod g of x, if I have no remainder, say g of x divides, and if has no divisor other than itself or 1, that has g of x has no divisor, that means g of x is now what we call that is a irreducible polynomial or a prime polynomial. So in the case of arithmetic modulo, an irreducible polynomial forms a field. So what is the thing we need to understand from this is, when I am going for a polynomial division, how we can represent as similar to that of your normal integer, but the condition what we can able to understand from this is, when I am taking a particular function dividing by another function, I am getting a remainder. What is the important thing we can able to understand here is g of x must be a prime polynomial or irreducible polynomial. So what is prime polynomial? That is either it can, that is g of x has no divisor other than itself and 1. So arithmetical modulo can irreducible polynomial form a field. So that is what the important thing when I am going to deal with a polynomial. Polynomial GCD, as you know, where we already practiced with the help of our integers, GCD of a comma b of x. For example, I am taking two functions, so I will get a common divisor, that is what c of x. Already we have discussed about the Euclid's algorithm. Okay, similarly we proceed. If I am pausing a of x and b of x, if b of x is 0, then I am written a of x. Otherwise I will go for recursively perform an operation, I will get the particular value. So modular polynomial arithmetic can be computed in Galois field of 2 power n. So what we will do, we will take a polynomial with coefficient of modulo 2 and whose degree is less than n, then we can able to form a finite field. And also we can able to find this with the help of inverse, that is with the help of extended Euclidean algorithm, similar to that of what we practice with the help of your integer. So this is an example we is explaining about when I am taking a Galois field of 2 power 3, how this is going to be executed with the help of your modulo irreducible polynomial of 2 power 3. The modulo irreducible polynomial of 2 power 3 is x cube plus x plus 1. So we can able to do the addition operation as well as multiplication operation, where you can able to say that always it is going to be, as in the case we can able to say that irreducible arithmetical modulo and irreducible polynomial forms a field. So here also we can able to see that when I am performing an addition with respect to modulo of x cube plus x plus 1, it is going to form a field. Similarly it is also going to form a field with respect to that. Okay. So how it is performed here is, as I already mentioned, addition becomes XOR. That means if both the inputs are same, I will get 0 as the output. If both the inputs are different, for example, I will get 0 0, I will get 0 as the output when I am going to perform. So when I am going to perform an addition, normally it is going to be an XOR operation. So we will take this particular case, if I take a x plus 1, okay, then I will get x plus 1. For example, this case, okay, x square x plus 1, then it is going to be an XOR operation. So 0 0 0 1 1 0 1 1. So XOR of 0 1 1 0 1 1, what I am going to get this particular case is x square plus x plus 1, that is, what is this? This term is represented by 1 1 1, that means I am getting 1 1 1, that is 1 1 1 is nothing but your with respect to the modulo of x cube plus x plus 1. After finding this value you will get that. And also multiplication is shift and XOR operation. So modulo reduction can be done repeatedly, substituting highest power with a remainder by irreducible polynomial. So with this we come to the end of this session. Outlines the different algebraic structure. We already discussed about the group, ring and field. In this session we discussed about the ring, what is a ring, what are the property of ring, fields, and also we discussed about the importance of the structure in the cryptography and various examples related with the field structure, how we can able to use in the case of cryptography. Thank you.